What we want to do today is show an implementation of this digital twin technology. Digital twins are a new notion, relatively. The idea is that the twin is a virtual copy of a real machine. So whatever the real machine does, the digital twin does. It can be with CNCs, with robots, with metrology equipment, and so on. But the most common kind of programmed machine tool on the floor today is the CNC, so we're doing it for the CNC. What you can perhaps see is that you can see certainly the real-time tracking, and at the same time there is the underlying machine tool, and in a moment it will get to the end of the path, and at the same time both pieces of equipment, both the virtual copy and the real copy should move. So we'll see if that happens. Yes, good. We've only just finished giving this demonstration to a group of Boeing people, so we are not doing the actual machining because we couldn't change the setup in time. We're just doing what's called a dry run machining, which is why the machine tool is above the part in the webcam, but we're showing what actually would be happening if it was not offset on the twin line. So what is our environment here? We have the digital twin software that is running or tracking the model in real time. This is connected up to the CNC machine by a protocol called MT Connect, which is popular in the USA and growing popularity in the USA as a protocol. It's an XML format for reporting manufacturing results in real time. So each time there is a movement, no matter how small, in fact at 100 Hertz, each time there's a small movement, it gets communicated to the digital twin, which then uses it to update a step model of the part. The step model can come from a CAM system, it can come from CAD systems, it goes into the twin, and the continuous simulation keeps a real-time measurable model of the manufacturing, which is a new thing, relatively speaking. Plus, we have smartphone technology, so that the browser, this is just this particular one is Firefox. Okay, Firefox on this one. We got Chrome on the other one. It works in Safari, etc. Is showing the machining in real time, right down to the removal level. If I go ahead and simplify the view a bit, I'll get rid of the machine, get rid of the toolpaths, and even get rid of the tool. You should be able to see the continuously updated model of the machining. And from this we can do all kinds of things, including calculate the chip thickness, which is one of our new capabilities we're going to be talking about today. So any questions about the general framework? Okay, so why are we doing this? There's a number of things that you can do with a digital thread to make manufacturing enterprises more efficient. The first thing is that you can use it to reduce costs, because you've got a continuous model of the manufacturing. That model can go into services in the cloud. So we'll be showing a service that generates new solutions. So if you look at this and say, hey, it's taking too long, I could do a bigger depth of cut with a stronger tool. We can go ahead and communicate that requirement to a CAM generation service that then sends back a new solution. Other services can help you select the machines, the cutters, the balance, the work, etc. What this means is instead of having to have many copies of CAM systems, one for each engineer, you have one cloud service. Second thing that digital thread gives us is it starts enabling the use of scientific methods on the shop floor. Okay, today you have a skilled operator. That operator understands machining, understands his machine. There's something called a feed override button on every machine. You can use it to make it go faster or slower. You need that if you suddenly need to complete the job more quickly. With this continuous modeling, plus our understanding of the tolerances on the part, for example, there's a flatness tolerance, semantic tolerance from the AP 242. With that modeling and that information, we can go ahead and determine via an algorithm what is the best speed to use. If there's lots of time, then you drive as gently as possible. If, on the other hand, you came in this morning, something else went wrong in the plant, and now everybody's waiting for your part, you dial it up and go as fast as possible within the constraints of the tolerances. That kind of analysis becomes possible with these digital models. The digital model allows for real-time measurement. At any moment, I can go ahead and ask for a model of the simulation to be stored as an STL file, and I can send that off to a measurement service. And we will demonstrate that in a little bit more detail as we go through. So we can adjust processes, we can validate changes. We're not showing it yet, but eventually we could do what's called closing the loop. Taking that real-time measurement that you're getting from the metrology device and use it to dynamically adjust things. And another key advantage is that you get the virtual model immediately. If it happened in some manufacturing plant hundreds of miles away, that model can be shipped to you and you can use it in assembly simulation. Finally, and perhaps most importantly, the digital thread helps you improve the product. Everybody gets to see what's going on. If this is happening on the weekend, you could phone the planner. The planner could go ahead and dial in, take a look at the process, not just perhaps the currently executing process, but the next operation of the process. The machinist could ask a question about it. They could resolve the issue, and the machining could continue without the planner ever having to leave the beach or wherever he is. And not only your internal people, but also external people. People like Sandvik, machine tool vendors, they have a great deal of expertise that you can dial into by sharing these models.
Before you move on,
yeah.
if it's okay, I'd like to ask you a question that I'm sure you're not expecting. So just to make sure that we all understand what's going on with the link between the machine tool in Renton that's moving and what's going on here. What would happen if the operator slowed the feed rate down, the feed rate override on the machine?
We should see the simulation slow down. So let's go ahead and do that. Rich, can you go ahead and call him?
Tell Stedman to slow it down. Put him on speaker so we can all say hello.
Put the tool back.
Hey Chris, say hi for up here. Look at Theo.
Hi, Stedman.
Feed rate down to 50%.
Okay, so it has visibly slowed down.
So that was that faster was a rapid feed.
Okay, yeah, go ahead and crank it back up to 100%.
Okay, back up again.
We can see a shadow.
Okay, so where is Chris? Chris is in the 737 plant, which is 30 miles away in Renton. Boeing has basically split into two major facilities in Seattle. Up here they do the twin engine, twin aisles, and down there they do the single aisles. That machine has got an empty connect export on it. Most machine tools do have empty connect exports on it. It's an entirely ordinary machine with just one out of the ordinary feature, which is it's got a very high communication rate for its empty connect. You don't typically get 100 hertz on empty connect for most folks, but Akuma does deliver 100 hertz for their empty connect. So 100 times a second, we're getting the updates which are going into the digital twin. The digital twin is maintaining that model that then gets sent out through the VPM as regular HTML5 that then gets rendered on the in the browser using ordinary normal technology. The only special thing being that we did have to work quite hard to enable the deltas to happen in real time.
Deltas meaning what?
Meaning the changes to the model. This model is being constantly changed as material is being removed. Yes?
Are those machine coordinates or part coordinates that it's sending back?
The empty connect is sending back both, I believe. Is that correct, guys?
Work offset coordinates.
Work offset coordinates. Yeah. Okay. And the step in C captures the machining in part space, which then gets converted into machine space.